I will go to the second lecture of this 11th week, and in this lecture we will be doing the most important idea in electronic structure of solids, that is that of Bloch theorem. So, week 11 lecture 2 we will be talking about Bloch theorem. To give you a perspective, we have been discussing about free particle wave function, okay. And one of the things we will do when we are dealing when you are doing the Bloch theorem is to go beyond free particle wave functions. Now what did we mean by free particles? Okay, free in what sense? So, it is free in the sense that it does not experience any potential except the confining one. So, that is what we meant by free particles. So, in the sense, what we mean is that these electrons or these electrons were treated as free particles. That means, if this is my crystal, okay, then the electrons are treated as particles that are just freely moving within this box. Okay. So, they were treated as so the free electrons, they are just treated as particles that are moving within this box. Okay. So, it is in that sense that they are free and they do not see any potential, they do not interact inside the box, the potential of interaction is 0. So, inside box u of r, which is the potential energy, shell energy function equal to 0. So, that means inside the box the particle does not feel anything and it is a free particle inside the box, but there is still the confinement, okay. Still confinement is there. So, the confinement effect is quantization of energy level. Okay. So, the energy levels are quantized because the particle is confined to be within this box. Okay. So, the particle is confined to be within this box, but so that makes the energy levels quantized, okay, but inside the box it does not have any potential of interaction, okay, and this is like a particle in a 3-dimensional box. Okay. So, now what we want to do is we want to go beyond these free particle wave functions. Okay. What is it that we want to say? What we want to say is something like this. I will just show this. I will just show this using a 2-dimensional picture. What we want to say is that inside this box there are lots of atoms, okay, and I will show them as positive charged species because we took out the valence electrons. So, what is left behind is ions, okay, and they form some lattice, and let me just draw a lattice for example. Okay. And so what you would like to take into account is that because of this lattice, okay, there are two things that will happen. The first thing is that the electrons are not free anymore. Electrons are not like free particles. So, what you had here, okay, electrons are moving freely, now they do not move freely. Okay. So, the two effects due to lattice. Okay. First one is that electrons are not free anymore. That means the potential is not 0. So, that is u of r is not equal to 0 inside box. Okay. That means at various positions the electron will feel some potential. The second probably more profound effect that is there is that this is due to crystal lattice okay. There is a periodicity okay. So, there are periodicity is imposed effects okay, and this is probably the more profound one which we will be discussing in lot of detail okay. So, what it means is that u of r is equal to u of r plus some lattice translation vector okay. So, r belongs to Bravais lattice. Okay. That means what we mean is that the potential experienced by the electrons okay. So, whatever it experiences here will be the same here, it will be the same here, it will be the same here, it will be the same here, same here and so on. Similarly, whatever it experiences in let us say this point will be the same as what is experienced here, it will be the same as what is experienced here. This is just due to the periodicity of the Bravais lattice. Okay. So, what it means is that your potential is a periodic function with a period of the Bravais lattice, and in general this is a 3-dimensional lattice, and so it should be true in all dimensions, all 3 dimensions. So, in general if you take a point okay, and you look at this point and this point, they are related by a lattice translation vector. Okay, they are related by a lattice translation vector. So, if 2 points are related by a lattice translation vector, similarly if you take this green point and you take this green point all the way here, okay, these two are also related through some lattice translation vectors. Okay. So, there is a lattice translation vector for that connects each green point to every other green point, and so you immediately conclude that the potential energy is a periodic function where with the periodicity of the Bravais lattice. So, these are the 2 effects, and today first I will be talking about just this effect. So, this is the effect that we will be talking about for most of today, and then we will also be saying that of course, we will be saying that u of r is not equal to 0, okay. But the interesting results will come because of this periodic nature of the Bravais lattice. Okay. Now, notice we used a box. Okay. Now, the size of the box was taken as Lx, Ly and Lz. Okay. And we will see how this size also imposes a periodicity. Okay. So, let us now go to the next point. Okay. So, the Bravais lattice introduces a periodicity. Okay. And what we said is that u of r is equal to u of r plus r. Okay. That is the potential energy. You expect in fact you expect all functions, other functions of space will be periodic, will also be periodic. So, if you have a scalar function of space, then it should be periodic. So, this is what you expect. Now, I also mentioned that there is a periodicity that comes from the overall size of the cell, and let's look at this. So, we have this overall box. Okay, and again this is Lx, Ly, Lz. Okay. Now, we in the free particle solutions, okay, we imposed a condition that the wave function should be same at the 2 boundaries. that the wave function should vanish at the boundaries, and that is how you got the free particle solutions. Okay. Now, what we will do is we will this we can take this lattice parameter Lx, okay, and Ly and Lz, okay, as integer multiples of the unit of translation. Okay. So, this is the unit of translation of the Bravais lattice, okay, and this can be I will call it A1, A2, A3. Okay. So, what we are saying is that the Lx is taken as an integer multiple. So, Nx is an integer, okay, and this A1, A2, A3 are basically the lattice translation vectors of your Bravais lattice. Okay. So, the magnitude of each of the lattice translation vector, magnitude of this is A1, this is A2, A3, this is the unit cell of corresponding to the Bravais lattice. Okay. So, what we are saying is that we are going to take this length. Okay. So, this length is typically many times the length of the crystal is many times that of the unit cell. Okay. And what we will do is, for simplicity, we will take this length as an integer multiple of this lattice parameter. So, Nx, Ny, Nz are all integers. Okay. Now, what that implies? Okay. So, that implies, if you look at this quantity, I will write this quantity right now, and then we will worry about it a little later. Okay. Now, another restriction that is put is that your functions are chosen to be periodic with Lz. Okay. So, there is a different periodicity. So, periodic boundary conditions on the entire system. Okay. That means any function, for example, the wave function of x, y, z is equal to psi of x plus Lx, y, z, y if you want you can take y plus Ly, and z plus Lz. Okay, it's you can do one or two. You can take any in all directions. In all the directions there is periodicity. Okay, so let me put these in brackets. So you might just take x plus Lx, or you might just take y plus Ly, or you might just take z plus Lz. Okay, and keep the others the same. So in other words, so what I want to say, psi of x plus this is same as psi of x plus Lx, y, z, and this is same as psi of x, y plus Ly, z, and so on, and you can make two of them different. Okay. So, basically you are saying that all functions are periodic with this overall system size. Okay. This is a tool. This is also referred to. Okay, this is a general tool that is used, general principle that is used. This is also referred to as the Born von Karman boundary conditions. Okay. Now, what this imposes is that we will see what this imposes. It says that if your wave function has to be a periodic function, that means whatever the value of the wave function is here, it should be the same value here. Okay. Now, if that has to be true, then your wave function, whatever it does in between, it should come back to here. Okay. And there is a typical function that is periodic with this is either a sine or a cosine function. So, suppose you have a sine or a cosine function, then it could be periodic. This is not periodic. So, it could be periodic okay, provided the wavelength of the sine wave is wavelength multiplied by an integer gives you the overall length of the system. Okay. This is what we will see. Okay. We will see how this bond 1 carbon boundary conditions affects the choice of wave functions. Okay. Now, let us go to the Bloch theorem, which is the central idea, okay, of this lecture. So, here what we say is that if we treat electrons as independently moving in the field of the ions. Okay. Then you can write the total wave function, which is a function of coordinates of all the electrons, as a product of coordinates of each of the electrons. So, you can write it as a okay, where 1 is supposed to represent a coordinate of first electron, second electron, and so on. Okay. So, 1 is equivalent to R1. This is a wave function of I will write psi 1 of 1, psi 2 of 2, psi n of 1, okay, and so on. So, what I am trying to get at is now we can write an effective 1 electron Schrodinger equation So, if you just look at one electron, if you just look at any one of these electrons, okay, then it satisfies an effective 1 electron Schrodinger equation that is written in the following way. So, there is a kinetic energy of the electron, that is minus h cross square by 2 m e, okay, times the Laplacian square. So, the kinetic energy in 3 dimensions is given by this Laplacian or the square of the gradient, plus u of r. U of r is the potential that is felt by the electron, okay, u of r. Now there is only one coordinate, there is only one electron, and you just have some wave function. Now, let me, so times psi of r, this should be E times psi of r. Okay. This is a 1 electron wave function. This is a wave function for a single electron that is moving in this potential u. Okay. So, such an electron is called a Bloch electron. Okay. And it is basically moving in this field of these ions. And now there is a theorem. Now we go to the Bloch theorem. So, Bloch theorem says okay, so this is let me remind you that that we have the condition, the periodicity u of r is equal to u of r plus r, okay, r where r belongs to the Bravais lattice. R is some lattice translation vector. So, now you can see what we have here. What we have is a kinetic energy term and a potential energy term, and that potential energy is periodic with the periodicity of the Bravais lattice. So, if you have such and this kinetic energy involves a second derivative. So, if you have such an equation, okay, then there is a general theorem which is called the Bloch theorem in solid state physics. It says that your wave function, okay, and let me, I will write it explicitly in terms of indices. N k, k is a vector of R is equal to e to the I k dot R u n k of R. Okay. So, I will tell you what I mean by this n and k. Okay, we'll see that n is like the nth. So, whenever you have a Schrodinger equation, okay, and you solve it, you will get several solutions. So, you get not just one solution, but several solutions. Okay, and n, and so this n index, okay, that is used to say which solution you are looking at. Okay, and now what we are saying is that you can write a general solution in terms of this k. Okay, in terms of this wave vector k. Okay, so the general solution can be written in terms of this wave vector as a product of two terms. The first term is just e to the I k r. There is a travelling wave. Okay, this is a travelling wave solution. Okay, this part is a travelling wave. The second part is some function of r, okay, and there is a restriction that this should be periodic. Should be equal to u n k of r plus r, where r is capital R is any vector in the Bravais lattice. Okay. So, what it says that the wave function for these Bloch electrons, okay, with the solution of this this equation, this equation is called the Bloch equation. So, Bloch equation is the effective one electron Schrodinger equation. Okay. So, this Bloch equation and the solution of it according to Bloch theorem can be written in this form, can be written as some travelling wave times a periodic function. Okay. And there are several solutions, okay, each indexed by this letter n. Okay. So, if I just go back and write this equation again, write the Bloch equation in a slightly more illustrative way. So, u now I can write psi n k of r is equal to epsilon n psi n k of epsilon n k. Okay. So, I am just writing the same Bloch equation in a slightly more explicit form with the indices n and k. Okay. And as I said k corresponds to this particular wave vector, okay, that is there in the solution. K corresponds to the wave vector that is there in the solution. Okay. Now, what does this imply for the first we will see what it implies for the Born-von Karman boundary condition. So, we can write. So, we are going to use a periodic boundary condition. So, that says that psi of x, y, z should be equal to psi of x plus Lx, y, z, Okay, so this is the the bond von Karman boundary condition. Von Karman boundary condition. Okay. And what this allows us to write, now if you go back and substitute the form of psi. So, if you substitute this form of psi, so what you will get is that you will have a term that looks like e to the I k dot r. Okay. Now, and you will have u and k of r. Okay. This should be equal to, now if I change x to x plus Lx, okay, then k dot r, okay, will look like the following. So, so if I use k dot r equal to kx x plus ky y plus kz z, then you will have k dot r plus Lx I. Okay, that is like changing x to x plus Lx. So, this is equal to kx. Now instead of x I have x plus Lx. Okay, so I will write the x term, okay, and I will write the plus kx Lx. Okay, the y and the z term will remain as they are. So this is equal to, so now the first part is just k dot r plus kx Lx. Okay. So now what I will write this as, so e to the I k dot, so on the right hand side I will have e to the I k dot, I will write kx Lx multiplied by e to the I k dot r, okay, and I have u n k of r plus Lx I. Now, remember we chose our Lx to be nx a. Okay. This implies that Lx times I is equal to nx times a I. Okay. And so it is just a times I multiplied by nx. So, this is a vector of the Bravais lattice. Okay, so this is a vector of the Bravais lattice. In other words, since we said that the Lx is nx times a is just an integer multiple of a, so a translation by Lx is also a translation in the Bravais lattice. Okay. So what that will imply? That will imply that u n k, and that will imply that these two terms are equal. Okay. So according to the Bloch theorem, these two terms are equal. Okay. So then we get a condition. So this gives you a condition that e to the I kx Lx equal to 1, and similarly we can also get conditions for ky Ly and kz Lz. And so if e to the I times something is 1, okay, so this implies that kx times Lx should be an integer multiple. Okay, I will call this m1 or mx. Mx is an integer multiple of 2 pi. Okay, so it should be 2 pi times an integer. Okay, then you have exponential of I kx Lx equal to 1. Okay, and this implies that kx should be equal to 2 pi mx by Lx. Okay, and what this implies is that the k, all the k's should be, so in general you can write your k vector as Lz k. Okay. Now, notice that I have assumed, okay, I should mention this clearly, that I have assumed orthorhombic unit cell. Okay, so in other words, alpha equal to beta equal to gamma equal to 90 degrees. Okay, this just makes the calculations easy. I can talk in terms of unit vectors I, j, k. Okay, so I have made this assumption. Okay, now what it says is that your k has to satisfy this kind of relation. Okay, so this is an important result. Okay, and I can further if I take if I replace L by nx a, okay, then I can also write this in terms of mx by nx and so on. Okay. Okay, so I won't bother doing that, but basically we can see that something like this should be true. Okay, so now let me go to the dispersion relations and the band index. Okay, now what this says is that your wave vector. Okay, now usually you would expect Lx to be quite large. Okay, in your nx to be a very large number. So the crystal is likely to be very big. Okay, so your mx by nx will be a very small fraction of a. Okay, so so what you would expect is that your k, your allowed values of k. Okay, so the allowed values of k are basically I can write as 2 pi. Okay, now if I'll write it as mx by nx, 2 pi divided by a by b mx or a1, a2, a3. So these are the allowed values of k, and these are fairly closely spaced because mx can go from 0 to infinity. Nx is likely to be a very large number. Okay, so these are going to be fairly closely spaced. Okay, the next thing is that if you just look at your Bloch equation, so you have let us say I have psi n k of r is equal to, now I will write this as E n k, just make sure I use the same notation, I use epsilon. So let me write this as epsilon n k epsilon in k is not a function of r times. So, now for each allowed value of k you have some energy. Okay. So, let me write this in a slightly different way. I will write this as epsilon n as a function of k. Okay. So, for each allowed value of k you have some energy associated with it and you have various energy levels. So, n is called the band index. Okay. So, when you solve this, if you could imagine solving such an equation, okay, then what you will get, the solutions will look like epsilon 1 of k, epsilon 2 of k, okay, and so on. Okay. And now suppose I make a plot of epsilon versus k. Suppose I make a plot of epsilon versus k, okay, and I'll just show it schematically. So so we'll come to the boundaries, okay, little later we'll describe this, but if you just make a plot, then you will get some energy. So, for each value of k you will have some energy, okay, for a different value you will have some energy, and if you join all these, okay, let me mention that k can take several values. So, these are the allowed values of k, okay, and I am just showing as though you were in a one dimensional system, but you can do this in 3 dimensions too. Okay. So, you have several values of k that are allowed. Okay. These are the allowed values of k. Okay. Remember, k has to be this of this form. Okay. So, it has to be 2 pi mx by nx a1. Okay. So, it has to be a integer multiple of 2 pi by lx, a1 times nx is lx. So, there are only certain values, but actually it is a very large number of values. Okay. These values are very closely spaced, and for each of them you will have some energy. Okay. So, if you look at epsilon 1, okay, let me this is for epsilon 1. Epsilon 1 will have all these values. Okay. So, this is and epsilon 2. So, this is epsilon 1 of k. If I look at epsilon 2 of k, it might look something like this. Okay, and so on. Okay. Now, what you see from here is that epsilon 2 has a range of values. Okay. So, this is a range of values of epsilon 2. So, epsilon 2 can be anywhere in this range of values. Okay. Similarly, epsilon 1 can be anywhere in this range of values. Okay. So, there is a range of values of epsilon 1 and epsilon 2. We will come to this boundary condition in the we will come to this part in the next lecture. Okay, what we mean by this. Okay, this is actually minus pi by a1 and this is plus pi by a1. Okay, we'll come to this. This is actually the first Brillouin zone. Okay, but we'll just show explicitly that you only need the wave function or the energy relation in this region. Okay. Now what you see is that this set of states are closely spaced, and this is called a band. Okay, this is also a band. Okay, so there's a band of energies. So you say that this whole range of energies is what is called this band of energies. Okay, and this comes because your wave function as a function of k has this kind of behavior. Okay, now n is called the band index. Okay, and this relation the relation epsilon n of k, okay, this relation is called the dispersion relation. Okay, and this basically tells you how this epsilon changes with k, how this energy of the nth band changes with k, that is called a dispersion relation. Okay. So we have qualitatively seen how bands appear in this case, okay, and so this is the qualitative origin of bands. So we have seen the qualitative origin of bands, okay, and in the next lecture we will see this more quantitatively. Okay, we will see this qualitative origin of bands, okay, that just comes from this dispersion relation, and we will see this more quantitatively in the next lecture. Okay. So with this I will conclude this second lecture of week 11. Okay. In the next lecture we will look at this in a little bit more detail, okay, and we will refine the band theory of solids. Thank you.